had to throw them away because they don't make sense having them as solutions. So, 3-5, the hard one. This will take a while. More graphing. Woohoo! You love graphing, don't you?
No.
I love making you graph.
I can
I know. So rational functions. Now, just like every other function we've dealt with recently, we started off with base functions. So I want to start off with what makes a rational function a rational function. What's the most basic form I can write? And the base function of a rational function, remember rational means fractions, is the easiest fraction polynomial top, polynomial bottom I can make. 1 over x. That's the most simplistic version of a rational function. So if I can figure out what's going on with this function, I should be able to manipulate it and see what happens with other rational functions. Polynomial on the top, polynomial on the bottom. So if I don't know how to graph something, how do I graph it? Cheater, you don't have one. So if you don't have a graphing calculator, how would you graph it?
In a table.
A table. So let's set up a table. Here's x, here's 1 over x. What numbers do you want to start with?
-1.
Go further.
3.
Not that far. How about -3? If I plug in -3 for x, 1 over x becomes -1/3. Go in order then. -2, -1/2. -1, -1. 0,
Undefined.
what was that? Oh, undefined. I was waiting for someone to say 0. Yeah, undivided is 0. Undefined. Cannot divide by 0. So that's one weird thing about a graph, because usually when we plug into a table, they're all very well defined. This one's not turning out that way. +1, 1. +2, 1/2. +3, 1/3. So that's all I'm getting out of integers. Not a lot of information. So let's graph it and see what happens. Plot our values. That's really crooked. Now, straighten that out of your papers. I can't draw straight off to the side. I have to stand right in front of it. Looks fine from here. Perfectly straight. All right, -3, -1/3. So you go 3 to the left, and down just a little bit. Squeaky marker. -2, -1/2. Down a little bit further. So maybe right about there. -1, -1. That should be right here. And then I have no clue what's happening between -1 and +1. We'll find out eventually. 1, we plug it in and we get 1. 2, you get 1/2. 3, you get 1/3. Okay. Now let's do a little analysis. Let's go with the positive side for a second. If I choose 10, it'd be 1 over 10. What happens to the value of the point? Gets closer to the x-axis, the line, right? The x-axis. So as I go further and further off to the right, this graph is going to keep on coming down. It's constantly decreasing. Will it ever touch the x-axis? No, because a half of 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 it. You could do that 1,000,000 times and still have some kind of value. Very, very small, but some kind of value. What value would it be really, really close to, though? You do a half of 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 a half. It gets really close to what number? 0, because it would be like 0.0000000 and then some change. So what we're going to say, mathematically, is this idea. It's called a limit. LIM is an abbreviation for limit. We say where x is going. Where's the domain going? Well, we're going off to infinity. That's somewhere off to the right. To infinity and beyond. And we're going to take our function and say what happens to it. So as x gets really, really, really big, the graph gets really, really, really small. And it gets so small that we can barely tell the difference between that and the number 0. So that's the mathematics of it. The interpretation is this. Means that x-axis is a I bet there's not 2 R's in horizontal. I love my double letters. Horizontal.
In between the A and S too.
It's called a horizontal asymptote. It's if you go off forever to the right, if the graph approaches a specific value, it could be anything, 1, 2, a half, a third, it really doesn't matter. It becomes known as a horizontal asymptote. 2 R's. Horizontal. Alright, my English language skills. Alright, let's go on the other direction. If I go to negative infinity, these values are going to be, as I move to the left, these values are going to rise, but they're never ever going to touch that x-axis again. So you get this graph that's coming up and coming up and coming up, but never ever quite touching that axis. It's a weird concept. The way I think about asymptotes is they pull the graph towards them, but they never ever touch. Do you know, my brother told me this a long time ago, when you take your 2 fingers and put them together like this, that technically they're not touching. There's a little electronic force pushing each finger away from each other. It's a little electronic force on your finger that makes iPads work. When you touch your screen and move it around, if you put a tissue on your hand or something like that and do the same thing, nothing happens to the iPad. So your finger has to touch it because it has a tiny, tiny electrical charge on the very surface of your finger. You didn't know that, did you?
You know we're going to have to try it
Yeah, if I clean my iPad with a shirt all the time. You know, I'll pick up a shirt and just wipe it down, and it does nothing. You start moving your finger around, and it starts doing what it's supposed to do. It's because you have a charge on your finger. Oh well, little things that you don't want to know. But technically, your fingers don't touch because they repel each other, and you only feel like they're touching because your nerves can sense what's going on, but they're technically, physically not skin to skin. Isn't that weird? He was an electrical engineer, so he understands charges and all that fun stuff. I shouldn't say was, is. He's not dead. Alright, my problem, oh, that's why I picked up that marker. My problem is, what happens between positive 1 and negative 1? So what I have to do is choose smaller numbers to see what happens. So...
You know where across the y-axis? No, are you talking about which one are you talking about?
Well, instead of just choosing integers, I'm going to start choosing fractions. Pick a nice number between negative 1 and 0. Negative a half. If I take the negative half as my domain, what's my range become? Negative 2. Pick something smaller than negative a half. Closer to the origin. Negative? That's going the other way. I want to come, which one? Yeah. Well, towards the origin, Absolutely less. No sign necessary. Between negative 1/2 and 0, pick a number. Oy, never mind. Negative 1/5. If I take the reciprocal of negative 1/5, it becomes negative 5. Negative 1/10. Oh, did you say negative 1/4?
Yeah.
I thought you said negative 4.
That's what I said, what's wrong with it?
You're mumbling.
I was thinking, like, was that seriously wrong? That's what I was thinking.
No,
Like,
I
I know
just-
it's not bigger than a
I just
half.
can't hear you. I remember I'm deaf and you all whisper and mumble and all that fun stuff. Negative 110. Negative 10. Alright, so plot those as well as best we can. So, negative 1/2, right about here, goes to negative 2, which is right about here. Negative 1/5, or negative 1/4, whichever, would go down to negative 4, which would be like right here. So as it goes down, it would keep going down forever and ever and ever. You know, put in negative 1/100th, it would go to negative 100. But it would never ever touch the y-axis because at the y-axis it's undefined. Same thing would happen on the other side if you chose positive 1/2, positive 1/4, positive 1/10. You'd have 2, 4, and 10 to contend with, and it would go up the y-axis on this side. So you get something that looks like this. This is the graph of 1 over x. All right, it's doing that approaching thing again along the y-axis. In this case, where a rational function is undefined, this becomes, I should be clear about this. After simplification, if a rational function still has points of undefinedness, these become vertical asymptotes. The graph can never, ever, 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 ever cross a vertical asymptote. Horizontal asymptotes, on the other hand, they can cross as many times as you want them to. They just have to get close to it. I have a nice picture of one of them up here. This thing has a horizontal asymptote, but it goes back and forth across it infinitely many times. But as it goes further and further to the right, it gets squeezed in, top and bottom, to the x-axis. So it's kind of a neat graph. So horizontal asymptotes, you could have a graph that has this as a horizontal asymptote, you know, 4, 2, whatever it is, and the graph itself would look something like this. And as it goes off to infinity, it just keeps squeezing in on that dotted line, but it crosses it infinitely number of times. So don't think because you have an asymptote that you can't cross it. All it means is it's going to pull the graph into it. It's like a magnet. The only one you cannot cross are vertical asymptotes because they are points of undefinedness. Totally different. Does that make sense? Okay. This graph has a fancy name. Hyperbola. It's called a hyperbola of the family of
So what time
conic
is it? I was
sections.
thinking what time it was.
The family of conic sections, hyperbola, just like a parabola. Parabola is also a family of conic sections. All right, very simplistic, right? So when I say, what does the base graph of a rational function look like, all you need to draw is hugs the y-axis, hugs the x-axis. Hugs the y-axis, hugs the x-axis. And you get a hyperbola.
Will it ever go on the other sides?
If you put a negative in front of it, it would flip. And if it would flip, it would be in the second quadrant and the fourth quadrant. Isn't that cool? Ah. So what about I have a base graph now. I should be able to do transformations on it. Here I have a graph g of x equals 1 minus 1 over x plus 3. What transformations were done to our base graph 1 over x?
Very negative.
Hmm?
Very negative.
What does that mean?
It's going the other side instead.
Oh, it's flipping over the x-axis. So the negative is saying flip over, I usually just call it the horizontal. right, what else is going on? Has it been that long that we've done transformations of functions? What else has happened to the graph? Oh, take it apart one by one. What's the 1 doing here, sitting out front? Mm. 1 would do nothing for stretching because it's 1 times anything is itself. But this is 1. It's actually plus 1 if you want to think of it that way. Moves it up 1, you said? So this 1 here, up 1. What's the 3 doing? Right 3, left 3. Which one? Left 3. Inside the function, it goes opposite direction. Remember, these long lines are parentheses. And if it's inside parentheses, it goes opposite direction. So that 3 is left 3. And then we can graph it. Or sketch it. Now remember, sketching, you don't want to plot points. You just want to throw the graph on a piece of paper. So, put my axes in. Where do I want to move? I want to go up 1. Here's y equals 1. A little crooked, but there it is. I want to move left 3. So here's x equals 3, x equals negative 3. And then I want to sketch my graph. Now remember, it flips over the horizontal, so normally it would be quadrant 3 and quadrant 1. But because it flips over the horizontal dotted line y equals 1, it's kind of going to be in this top left-hand corner and this bottom right-hand corner. So the graph looks like this. You get your translated hyperbola. Isn't that neat? Come on. Yeah, great. Awesome. No? So sad.
Wonderful.
Yay! The problem is, you're not going to see them like that. More than likely, what you're going to see is 1 term, 1 expression, rather than 2 separate ones like this. So how would I force those 2 to come together? What do I need to make 1 term out of these 2? Okay. How do you add a number and a fraction? Common denominator. What's the common denominator here? So this 1 becomes x plus 3 over x plus 3 minus 1 over x plus 3. And now that they have a common denominator, I can bring them together. So this becomes x plus 3 and x plus 2 in the top. Now, if you saw the function looking like this is still g of x. And I asked you to graph it, it becomes a little bit harder because it's not a transformation anymore, unless you separate it out, and that's really hard to do. A lot of people wouldn't be able to do that. But that graph and this graph are exactly the same. So I have to show you another technique that if it comes in this form, how would you come about graphing it? Now, some of the behaviors are exactly the same. They're going to have horizontal and vertical asymptotes, and if they have those asymptotes, they're going to pull the graph in towards it. Some other things that are going to help us, well, like for instance here, what's this point called? That point right there? What's it called? X-Intercept. Woohoo! So this is your X-Intercept. We could find that. We know how to find the X-intercept of any graph. That's real easy. Set it equal to 0 and solve for x. Then you have this point over here. What's this one called? Y-intercept. And we can find that, let x equal 0 and see what happens. And then the rest of it would be inequalities. When is the graph below the x-axis? When is it above? Does it cross the horizontal asymptote? More than likely not, but sometimes it will. And it definitely does not cross the vertical one. So it kind of gives you clues in how to graph this. By the way, what is the x-intercept of this graph? Anybody know? -2. Because the only thing that's going to make it equal to 0 is when x is equal to -2. What's the y-intercept of this graph? How do you find a y-intercept?
X equals 0.
Let x equal 0. If you let x equal 0 in this box, what happens? You get 2 over 2/3. So this must be 0 2/3. So these are the things that we're going to have to do. One of the hardest things to find is the horizontal asymptote. Because that is something weird. You have to do a upper level math thing called the limit. Is it time for break already? You're looking at your watches and stuff. Not even close. So let me explain how to find a horizontal asymptote. Vertical asymptotes are easy. Find when the bottom is undefined. So and let's see if we can find a systematic way of just cranking it out. Or maybe even a shortcut way. No, I won't show you the shortcut. What you're going to do is, if you're looking for a horizontal asymptote, you're going to say y equals, because it'll be a horizontal line equation. It'll be like y equals 2 or y equals 0. The limit as x goes to infinity of, let's say, 3x squared minus 2x plus 1 over 2x squared plus 4. Say this is our rational function we're trying to find a horizontal asymptote for. The trick is this. We know as a fact that this is equal to 0. We can kind of extrapolate a little bit. If 1 divided by basically infinity is equal to 0, then 1 over infinity squared is also equal to 0. 1 over infinity cubed would be equal to, well, 0. So if x has a whole number power on it, those are also going to 0. Now, technically they're not equal to 0, they're just really, really close to it, like neighbors, buddies. So the trick that I'm going to pull for finding this answer is divide by highest power of x. And see what happens. So you rewrite it as 3x squared over something minus 2x over something plus 1 over something all over 2x squared over something plus 4 over something. What is the highest power of x in this entire expression? X squared. So you divide everybody by x squared and simplify. So, what's 3x squared divided by x squared? 3. Minus, what's 2x divided by x squared? It is definitely not 2x. 2 over x. Plus, and there's nothing you can do with it, it's 1 over x squared. All over 2x squared over x squared. 2. Plus, and there's nothing you can do with it, 4 over x squared. And then there's this limit as x goes really big. As x goes really big. Alright. Well, here's the cool thing. Think of it this way. If you give $1 to Donald Trump, is he getting any richer? Sure, but does it mean anything to him? Now, if you give $1 to me, I'm going to be quite happy. Because, I look for quarters in my couch to go out to eat. Or I used to a long time ago. We'd find a couple quarters and go to McDonald's or Burger King to buy a burger. We'd be like, yay! Those are the days. So giving $1 to someone that's really rich is irrelevant. So, all these people trying to give tax breaks to the rich people, that is actually quite silly because they won't even notice the difference in their paychecks. Now, if they took more money out of our paychecks, you'd know it in a heartbeat, wouldn't you? Yeah. Okay, so what happens here is, as X gets really, really big, these three things are like giving $1 to Donald Trump. They're insignificant. They don't change very much. They get really, really close to, well, 0. So what we're going to say is all these things with X's in the bottom, any type of X in the bottom, they're all going to 0. As X gets really, really big, those numbers are going to get really, really small. So the only things left over that have any consequence whatsoever is a 3 and a 2. So this horizontal asymptote is going to be y equals 3/2. The graph is going to get really, really close to this line, y equals 3/2. Now there's a part 2 to the problem. I'm not sure if it works though. It might. Do I have time? I haven't looked at the time. Oh, it might work. This thing up here is a function basically, this rational expression. And I just told you that y equals 3/2. What should you go looking for? If I tell you y in a function,
X.
you should go looking for x. If I tell you x in a function, you should go looking for y. So I just told you what y is equal to. So you should take this value, this is a step that a lot of people forget, and set it equal to the original function. Find an x value so that y actually does equal 3/2. If you can find a value, that means it's a coordinate that the graph actually crosses the horizontal asymptote. And this is a very important little piece of information if you can find it. How would you solve this equation? What would you do first? What neat little trick pops into mind? Fraction equal to a fraction. What neat little trick in 8th grade did you learn?
Oh.
No. That's us. If you were given x over 3 is equal to 5 over 4, what trick did you play? Cross multiply. As long as you have a fraction equal to a fraction, you can cross multiply. So if we cross multiply these, 3 times that and 2 times that, you get 3 times 2x squared, 3 times 4, 2 times 3x squared, 2 times negative 2x, negative 4x, and 2 times 1. You get this nice little equation. What would be your first step of solving this nice little equation? You could, but what do you look at it a little bit more closely? Not sure if that's going to help because you can only combine on both sides. I think I know what you're talking about, though. They both have 6x squares on both sides, right? If you start shifting one side to the other to get it equal to 0, what's going to happen to the 6x squares? They're going to cancel out. Let's kill them first. What's left over is 12 equals negative 4x plus 2. Is that a quadratic? What's it called? Linear. And to solve a linear equation, move the 2 across. This becomes 10 equals negative 4x. And eventually x equals negative 5 halves. So this gives us a coordinate to work with. Negative 5 halves, comma, 3 halves. And this is a point on the horizontal asymptote. Point on the horizontal asymptote. And that sometimes becomes really important. Sometimes. To get the picture to look kind of nice. Alright, break time. Shoot. Next up, we'll be graphing an ugly thing that looks like that. The one you'll basically be asked a lot of information about on the test. And it looks like this. Graph. G of x is equal to 2x squared minus 3x plus 5 all over x squared minus 1. 1 Steps. You all like steps, right? Give you some steps. How to tackle this problem. Go for the easy stuff first. 1, find X-intercepts, Y-intercepts. Standard for pretty much any graphing of any function going, whether it be polynomial, quadratic, rational, anything that we're going to deal with in the future. 2, find vertical asymptotes. Any value that makes the bottom equal to 0, the denominator equal to 0, because you cannot divide by 0. That's what gives you vertical asymptotes. 3, find horizontal asymptotes. Using that limit as x goes off to infinity of the function and divide by highest power. Okay, so x-intercepts, y-intercepts, vertical asymptotes, horizontal asymptotes, and probably the most important part of this, do a number line test. Find out when it's above or below the x-axis. If you do all of these things, your pictures will look somewhat correct. I know how you all graph, and it's amazing. You could have the points all lined up for you, and you'd still miss them. It's just that artistic ability that people lack sometimes. Then other people draw cute little pictures throughout their whole test. She's not saying anything right now. So, that's what we're going to do to this g of x function. So, first off, x-intercepts. 1a. And this is probably going to take 2 boards because I'm expanding it out and going into small details about everything. If I want to find the x-intercept, what do? X-intercept of any function. Set y equal to 0. Or in this case, g of x equal to 0. So it becomes 0 is equal to 2x squared minus 3x plus 5, all divided by x squared minus 1. Let's solve that equation. Great. What do you do first? Getting that time of night when brains are turning off. How do you solve that equation? What's your first step? What don't you like about it?
We do the same thing like we did the last problem.
Yeah, sure, why not? What did we do for the last problem?
The x squared for the last one.
No, that's finding a horizontal asymptote. This is just solving a simple equation. That has a fraction in it. How do I get rid of the fraction? Multiply both sides by the common denominator. In this case, x squared minus 1. Why are you making things so hard? Oh, because it looks different, or it seems like it's different because it's in a different section of the... Stop that. It's math. It does exactly the same thing time in and time out. Multiply both sides by x squared minus 1. Now, the nice thing is the x squared minus 1 goes away completely. It's not even on the other side because 0 times it makes it gone. So basically all this is saying is The only way to make this rational expression equal to 0 is when the top is equal to 0. The bottom can't do it. So now you get this equation. 0 equals 2x squared minus 3x plus 5. How do you solve that equation? Stare at it. No, can't factor it, so what does that leave you? Complete the square, or I suggest quadratic formula. So, negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. Yes, you should have that memorized by now. Negative b plus or minus square root of b squared minus 4ac all over 2a. Why don't I have to go any further? Okay, go further. Negative 3 plus or minus the square root of do I look like a human calculator to you all?
30,
Negative 31.
Negative 31 all divided by 4. Do I have to keep going? Why? Huh?
You can't do the rational thing. 31.
I can keep going and come up with answers, but I'm trying to graph something in something that's called a rectangular coordinate system that works really on real numbers. These aren't real numbers. Why? What does this create?
A negative
It creates i's, which is imaginary. So this would be I squared of 31. This tells me that there are no X-intercepts, because my X-intercepts are imaginary or complex. So no X-intercepts. Even though we're not finding them, that's important information. That means the graph can never, ever, ever cross the x-axis. Won't even touch it. Won't even touch it. All right, so there's X-intercepts. 1b. 1b is easier. Y-intercepts. How do you find Y-intercepts of any function? It's like review.
You switch it.
No, it's not. That's like inverse functions. How do you find the Y-intercept of any graph? Set what equal to 0?
Equation.
Nope, that's what we did already. That's this one. That's X-intercepts.
Oh, X.
Set x equal to 0. Always the opposite variables. Let x equal 0. So we're evaluating the g function at 0. Well, g of 0 is equal to what?
You put the whole thing from the beginning, right?
Yeah, you go way back to g of x over here. What's g of 0? I'm going to sleep here. What's the final answer?
5
Final answer. What's 5 over negative 1?
Oh, negative 5.
Ah, negative 5. So, we have a y-intercept of 0, negative 5. Hey, it's like 14 simple ideas. Alright, switch colors. 2. Find the vertical asymptotes. So how do I find the vertical asymptotes of a rational function? I gave you a hint in my directions. Any value that makes the bottom equal to 0. So the hint is, take the bottom, do what with it? Set it equal to 0. The bottom is x squared minus 1. Set it equal to 0. It factors into x minus 1 and x plus 1. So this thing has 2 vertical asymptotes. One at positive 1 and another one at negative 1. Those are your vertical asymptotes. It's what the bottom can't equal. So they become a vertical asymptote. All right, that one's not easy. 2 is an easy one too. 3 is the trickier one. We need to find the horizontal asymptotes. That uses that limit thing and divide by the highest power. So you go y is equal to something that happens when x gets really, really big of, and the way you want to write it is 2x squared over something minus 3x over something plus 5 over something. Get it all set up for what you're going to do next. You're going to divide everything by the highest power of x that you see in this expression. What's the highest power of x? X squared. And you do it to everybody. Top, bottom, every single term. And you simplify the expression. Right? So this becomes y is equal to this ugly mess. 2x squared over x squared. 2 minus 3x over x squared. 3 over x. The last one can't simplify. Alright, over x squared over x squared. 1 minus, and this one doesn't simplify. Now, anybody with an x in the denominator, they become really, really close to 0. They become insignificant. So these three, since they have x's in their denominators, they all go to 0. So what's left over? 2 over 1, better known as plain old 2. So your horizontal asymptote is y equals 2. Not that bad, right? Now there's some trick problems. Like for instance, if the power in the top was less than square, then the top would equal 0 over a number, and 0 over a number is 0, and that would be the x-axis. That would be the x-axis. The other one is, what if the power is higher in the top and lower in the bottom? Well, then it doesn't have a horizontal asymptote. That's something else, but we're not going to deal with those. All right, now, part of 3 is finding out if this graph actually crosses the horizontal asymptote. So up here I said y is equal to 2. So what should you go looking for? X. And to find x, you say, well, if y is equal to 2, the x terms are 2x squared minus 3x plus 5 all over x squared minus 1. How do you solve that equation? Cross multiply, write it as 2 over 1 if you have to. So this becomes 2x squared minus 2 is equal to 2x squared minus 3x plus 5. Now, if it turns out that there is no solution, don't force it. I mean, if one side becomes equal to 0 and the other side turns out to be 5, 5 doesn't equal 0, so there is no solution. So if you get something really strange, it doesn't ever cross this asymptote. But this one, the 2x squares are going to cancel. They're on opposite sides, and they're exactly the same. So that leaves you with a linear equation. How do you solve negative 2 equals negative 3x plus 5? Subtract 5, that becomes negative 7 equals negative 3x. Or x equals 7/3. So this thing, when you put it together, gives you a coordinate 7/3, comma 2. Okay. Now here's the sad part. I have to erase all this. I'm going to rely on you for the information. So don't mess me up later. I'll know if you do. Because number 4 is still up here. We still have to do a number line test. That means I need to know all the zeros of this thingamajig. But there's really not that many zeros. Quote, zeros. Zeros of the numerator, zeros of the denominator. So, number 4, number line test. What are the only zeros of this problem? 1 and negative 1. The top doesn't give us any because they only had imaginary complex, complex roots specifically. So here's negative 1, here's positive 1. The hard part is going to be testing it. It's going to be testing it. So one thing we might want to think about is, If we look at the numerator, let me write it here, 2x squared minus 3x plus 5, is this thing, if it only has imaginary roots, it's either always positive or always negative, because it can't cross the x-axis. So plug in 0, that's a good test. This thing is always going to be positive. It's always going to be above the x-axis. So the only thing that's going to make this negative are the bottom factors, x minus 1 and x plus 1. So I really don't need to test the tops, because whatever number I plug in there is going to make it positive. But I'll still talk about it. So pick a number to the left of -1. -2. If I plug it into the top, it's going to become positive, so I just leave him alone. If I plug it into the first one at the bottom, it becomes negative. The second one, negative. So you get negative, negative. And positive, negative, negative is a positive. That means the graph has to stay above the x-axis to the left of -1. It can never, ever get below it. All right, pick a number between -1 and 1. 0. If I plug in 0 to the top, it's positive. If I plug in 0 to the bottom, first one it's negative. The second one is positive. So positive, negative is negative. The graph is always below the x-axis between -1 and 1. Then I pick a number bigger than 1. 2. The top is always positive. The bottom, positive, right? Because we're picking 2, which is bigger than 1. So this region is positive, always above the x-axis. Now we can graph pretty much what this thing looks like. I'm going to stand in front here and do it properly. Is that pretty straight? Horizontal? Vertical? Not bad. Alright, so here's 1, 2, 3, 4. 1, 2, 3, 4. Hopefully I have enough room because this graph goes down a little bit. All right. Putting information in. The first thing we found was X-Intercepts, which was none. So I can't plot anything on the X-axis. Next one was a Y-Intercept. 0, -5, way down here. Is our Y-intercept. The next bit of information was the vertical asymptotes. Step number 2. 1 and -1. I think it was vertical asymptote. No. Yeah, horizontal was next. So 1 and -1. So these are lines that the graph can never, ever cross. But the graph gets pulled in like magnets when they get close to these vertical asymptotes. So that's another property we want to look at when we're graphing this thing. Has a horizontal asymptote at 2. So that goes this way. Okay. And it crosses this horizontal asymptote exactly once where? Seven halves or 7/3? 7/3. So 7/3 is 2 1/3. Right? 2 1/3. So 1, 2, a little bit more, right about here. So that's 7 and 7/3, comma 2. 7/3, comma 2. Ooh, I should put this in blue too on here. Didn't need to put that in green. All right, so that is horizontal, vertical, point crossing horizontal, X and Y intercepts. What's left? Oh, the only thing left is the number line. Now, I don't know why the book chose not to do the number line method. It makes life a lot easier. All you have to do is a little analysis. Number one, between negative infinity and negative 1, this graph has to stay above the x-axis. There is no ands, if, or buts about that. There are two regions you can talk about. Remember, it can only cross the horizontal asymptote once. So over here, it can't cross the horizontal asymptote. The two regions you can talk about are here and here. And I'll erase these in a second. The graph is either in region 1 or it's in region 2, bounded by the green and the x-axis for region 1, and then that top left-hand corner. Out of those two, where does the graph have to go? It has no other option. Well, let's put it in region 1. If it's in region 1, it'll hug the dotted line from the top, and then eventually it has to go down. Why can't it go up? It'll cross that line, and we know it only crosses one point. That's why that becomes important. So it can't be in region 1 because it would force itself to go down, which would make it negative, but I know it has to be positive. So that leaves only region 2. Actually, I'll just leave those up there. So the graph has to be here, and it'll hug the horizontal asymptote, and eventually it'll start hugging the vertical asymptote. And look something like that. It has to go in region 2. All right. Now the graph is between negative 1 and positive 1. Where is it? Well, it has to stay below the x-axis. So here's a point below the x-axis. We can use that as a reference point. If the graph is going to go this direction, it's always going to go in that direction, right? Think about it. It's going to get sucked in by the horizontal or vertical asymptote. If it gets sucked in by the horizontal or vertical, I keep calling it horizontal, vertical asymptote, it's eventually going to cross the x-axis. Can't do that. There are no X-Intercepts. And then eventually it's going to become positive. So it can't do that. So the only option is to go down. That's what I mean by analysis. You see what happens, and if it can't happen, don't do it. All right, on the other side of that point, can it go up? No, for the same reason. Between negative 1 and 1, it has to stay below. So the only option is for it to go down. Now, that part of the graph, I'm not sure about its perfect picture. Right now, I have that 0, -5 as a maximum, relative maximum at that point, but it doesn't have to be. It could go, through this point, go up a little higher and then take a dip. That's possible. But without calculus, you would never know. So, just do a little parabola shape, you'll be fine. All right, the tricky part of the graph, this side. Above or beyond positive 1 to infinity, the graph has to stay above the x-axis. So that leaves you region 3 and region 4. Now this is where it gets tricky. But it has to cross that horizontal asymptote at this point. But don't let that mess you up. Try to put it in both of them, treat it like normal, and then see what happens. If I put the graph in 3, it's got to hug this asymptote and then dive down, right? Not necessarily, but we'll talk about that in a second. But it can't do that, right? So the majority of the graph better be in 4. But here's the problem. It has to cross at this point. But I know it has to go up here because as it goes up the vertical, I want it to stay positive. So the graph is going to come down. It's got to go through this point, cross to the other side. It's a linear factor. So it's just going to cross. But eventually it's going to have to turn around and come back up and approach this dotted line. Get really, sucked in by it. It's like a magnet. So this thing goes up forever, comes down, crosses this point, eventually starts coming back up. And it does like a little U-turn. But it never ever touches that dotted line. So this is the graph of g of x. Isn't that cool? Awesome? Pretty much. I got 20 minutes left. So maybe I'll be nice. Be nice? I can be nice. But rational graphing. All the pieces.